Scientists have just made a major discovery about dark matter in the early universe. By studying galaxies nearly 13 billion light-years away, they've found that dark matter played a much bigger role than expected. But how do we study something we can't see? What exactly did astronomers uncover about dark matter in these ancient galaxies, and why does this matter for our understanding of the universe? In this video, we'll break down the science behind this discovery, explore its implications, and see what comes next. The biggest challenge with dark matter is that it doesn't interact with light the way normal matter does. Galaxies emit or reflect various wavelengths: visible light, radio waves, X-rays, you name it. But dark matter stays hidden from all these signals. Still, scientists can infer its presence by looking at its gravitational effects. Think of it like a detective studying footprints at a crime scene. You might not see the suspect, but you can tell they were there if you know what the footprints mean. In the case of dark matter, one of the clearest footprints is how galaxies rotate. In simple terms, astronomers expect that if a galaxy is held together by only the mass of its stars and gas, rotation speeds should drop off once you look far from the galaxy's center. But observation after observation shows that speeds remain high, even out at the edges. That extra gravitational pull suggests an invisible mass component: dark matter. Now, studying very distant galaxies, especially those with quasars, gives us a unique chance to investigate the role of dark matter in the first billion years of the universe. Quasars are massive black holes that consume material at such a furious rate. They shine incredibly brightly. They stand out at large distances, effectively guiding astronomers to prime spots in the cosmos where early galaxy formation happens. By examining how gas moves, especially through certain emission lines, researchers can reconstruct the mass profile of these galaxies, teasing out how much of that mass must be dark matter. In recent studies, scientists rely on the Atacama Large Millimeter Submillimeter Array, ALMA, to observe emissions from ionized carbon, often called C2I. This emission line is particularly valuable for probing cold, dense gas in early galaxies. By mapping out how that gas rotates around the galaxy's center, researchers see how fast different parts of the galaxy move. Once they account for the galaxy's inclination and the distribution of its gas and stars, they can figure out how much invisible mass is needed to keep everything spinning the way it does. The result is a glimpse of the dark matter's role in shaping galaxies before the universe was even a billion years old. What's truly exciting is that many of these high redshift quasar host galaxies turn out to be dark matter dominated even near their centers. This is somewhat unexpected because studies of galaxies at slightly later times when the universe was roughly 3 billion years old often show that stars and gas make up a big fraction of the inner mass budget. In contrast, these new findings reveal a substantial amount of dark matter in the same region, sometimes approaching or exceeding 50% of the total mass. If you think of a galaxy like a big pie and you slice it around the center, you usually expect something like 2 slices of stars and gas, with maybe 1 slice of dark matter, at least in some galaxies in the slightly later universe. But these early quasar hosts suggest the dark matter slice might be bigger than all the rest combined. This could mean that these galaxies formed in extremely massive halos, concentrations of dark matter right from the start. Looking at how ionized carbon gas moves at large distances from the galaxy's center also lets astronomers estimate the size of the halo, a bit like looking at a spider web's outer threads to see how big the web is. From their observations, researchers infer that these quasar hosts likely reside in billions of solar mass dark matter halos. At such high redshifts, that's gigantic. It suggests these quasars live in the densest neighborhoods of the fledgling universe, where plenty of gas and stars can form quickly to feed a rapidly growing supermassive black hole at the center. Additionally, these results show that supermassive black holes in these galaxies might be overmassive when compared to their hosts' stellar content. Usually in local galaxies, black hole mass follows a certain ratio to the mass of the galaxy's bulge. Here, though, the black hole seems to be growing faster than the galaxy's stars. That rapid growth, coupled with a hefty dark matter halo, might be the key to understanding how some black holes reached a billion solar masses so early in cosmic history. It's fair to ask, why all the fuss about invisible matter in galaxies we'll never visit? The short answer is that dark matter underpins our entire cosmic framework. Our standard cosmological model, often called lambda CDM, says that structures in the universe form from the bottom up. Tiny fluctuations in the early universe's density grow into dark matter halos, which then pull in gas to form galaxies. So when we see large dark matter fractions in the earliest known systems, we're essentially watching these big lumps take shape. If these new observations had contradicted what simulations predict, it would shake our faith in the lambda CDM model, or at least force big revisions. Instead, what we're seeing generally lines up well with the idea that massive halos host the universe's earliest and brightest quasars. At the same time, the precise values of dark matter fractions or halo concentrations can either reinforce or refine our theories, offering a more detailed picture of how galaxies matured in their first billion years. From here, the James Webb Space Telescope can help identify the stellar part of these galaxies more clearly. By detecting faint starlight that might have been drowned out by a quasar's glare, JWST could give us better estimates of the galaxy's normal matter. Combine that with ALMA's refined measurements of gas and dust, and we might solve the puzzle of exactly how much mass belongs to each component: stars, gas, black hole, and dark matter. Moreover, deeper ALMA observations at higher resolution could map out gas even farther from the galaxy's center, where dark matter's impact is most pronounced. Meanwhile, large surveys could reveal whether these monstrous halos are surrounded by swarms of satellite galaxies, giving a fuller view of the cosmic environment. All of this will feed back into our understanding of galaxy evolution. We're still piecing together how galaxies at later times, like our Milky Way, formed and evolved from earlier prototypes. If the local universe is a photo album of grown-up galaxies, these high redshift quasars are baby pictures showing how quickly some galaxies reached adulthood. That, in turn, tells us a lot about how matter clumps and the timeline for cosmic growth. In the end, these studies highlight how dark matter serves as the foundation of galaxy formation. The interplay between massive dark matter halos and overgrown black holes likely explains why some galaxies appear so massive and luminous so early in cosmic history. Yet this is only the beginning. Each new discovery refines our understanding of when and how dark matter shaped the universe. As ALMA, JWST, and future telescopes continue to reveal its influence, we move closer to uncovering the unseen force that has guided cosmic evolution from the very start. Thank you for tuning into Amazing Space. If you enjoyed this update, don't forget to subscribe and hit the notification bell for more cosmic discoveries.